here we are. It's a recursive version of T-cell deltail, and the first thing I did was cut and paste on the iterative version. Okay, and we are going to transform our iterative version in recursive version, just so that you know. Generally, recursive versions tend to be simpler, and it will be just as easy for us to start with a recursive and transform it into an iterative version. So during the exam, or when you are assigned to use one specific programming style, do not feel confined to have absolutely to implement an iterative version before to move to the recursive one. I'm simply doing it in that direction because most of you are more familiar with loops, etc., that you studied already in your previous programming class than you are with recursivity. So this is kind of a scaffold for me to lead you to start thinking recursively. So once again, let's have a checklist here. This first test is valid. If my list is null, I don't have anything to delete as a tail. This is still true. And then there is a whole logic here of, well, if I am on the before the last element, etc., then I'm going to do something, and if my list has only one element, I'm going to do something else. Well, the good news is that with the recursive design, every time we call this function, we call it with T-cell ** list. We call it with, a pointer on T-cell, which means that if we are called with the address of the next field of the previous element and we find ourselves on the last element of the linked list, we can still modify that pointer. So this is one of the essential difference with the previous version. We're going to be able to simplify our code considerably. If you're not sure about what I just said, you need to absolutely post a question on the forum asking for more detail, and I'm going to leave that open so that I will see some activity on the forum on that topic, because this is a really important difference between the iterative and the recursive version of this particular function. So we have here our test when the pointer which address you passed to me, *list, is the last element of the list. Then I free this element and I set that pointer to null. So *list might very well be the next field of the previous element of the list, and we are going to exploit that. So if we are on the last element of the list, we deallocate it and we set the pointer that led us here to null. If we are not yet there, then we are going to simply call ourselves recursively. We are going to erase all of this here real quick, and we're going to say, well, let's move forward to the next element. And to do so, we are going to pass here the address of *list arrow next. So because I passed the address of this pointer, okay, I know that my current *list pointer refers to an element which is not the last one of the list. I pass the address of its next field, so that if I realize suddenly that this next field was null and I am here pointing on the last element of the list, I'm going to be able to modify this pointer. Okay, so let me restructure a little this to make it a little more readable maybe. And we are going to compile and test our recursive version. So, hold on a second. Actually, I will need the curly brace here. I'm just trying to make things here so that they appear like a list of cases pretty much. And then generally this is a good way to represent a recursive function, because it's always, if this condition, then do that, if this condition is do that, if this condition, then do that, etc. So let's try it. Control S. Saving the file right now. Let's move to the terminal. So we are working on the recursive version. So let's make sure we compile this one. A.out. We are adding to the tail, adding to the tail, adding to the tail, removing the last element, removing the last element, removing the last element. So we are doing exactly the same thing as the iterative version.